So, here's something worth thinking about as you settle in tonight. Right now, somewhere on this planet, there are about 440 nuclear reactors humming away, splitting atoms, boiling water, and pushing electricity out into the grid. They're doing it in France, in Japan, in the middle of Illinois cornfields, on the coast of England, tucked into the hills of South Korea. And most of the time, nobody thinks about them at all. They just work. Quietly. Which is kind of remarkable when you consider what's actually happening inside those buildings. A controlled chain reaction, atoms tearing themselves apart, releasing energy that was locked up since before the Earth existed. That's not a metaphor. That energy really is that old. It was baked into those atoms inside ancient stars, billions of years ago, and it's been sitting there, patient, waiting, in uranium ore buried in rock, until someone figured out how to let it loose. And the story of how we figured that out. That's what I want to walk you through tonight. Slowly. No rush. We'll start at the very beginning, with the people who stumbled onto the first clues without even knowing what they'd found. And we'll work our way forward through the breakthroughs and the mistakes and the wild leaps of understanding that got us to where we are now. Along the way, I'll explain how the reactors actually work, what's really going on inside them, why people worry about them, and why the engineering is so much more interesting than most people realize. But we'll take it easy. If you drift off somewhere around the discovery of the neutron, that's perfectly fine. The atoms will still be there in the morning. Let's start in 1895. A German physicist named Wilhelm Röntgen is working late in his lab in Würzburg. He's experimenting with cathode rays. Basically, he's got a glass tube with most of the air pumped out, and he's running electrical current through it to see what happens. Scientists had been playing with these tubes for years, but on this particular evening, Röntgen notices something strange. There's a fluorescent screen sitting on a bench nearby, and it's glowing. Not because he aimed anything at it. It's just glowing on its own. Something invisible is coming out of the tube and hitting that screen. He moves the screen farther away. Still glowing. He puts things between the tube and the screen. A book, a sheet of metal. Some things block the glow, some don't. And then he puts his hand in front of it, and on the screen he sees the shadows of his own bones. He calls them X-rays, because X is what you use in mathematics when you don't know what something is. He genuinely doesn't know what they are. Nobody does. But within weeks, the discovery is a sensation. Newspapers go wild. Doctors immediately see the medical applications. And here's what matters for our story. Röntgen's X-rays get other physicists thinking. If this tube is producing mysterious invisible rays, what else might be producing them? What other secrets are hiding just beyond what our eyes can see? One of the people asking that question is Henri Becquerel, a French physicist in Paris. He comes from a family of physicists, actually. His father and grandfather both studied phosphorescence, which is the phenomenon where certain materials absorb light and then re-emit it, glowing in the dark for a while. Becquerel wonders whether phosphorescent materials might also produce X-rays, so he designs an experiment. He wraps a photographic plate in thick black paper so no light can reach it, places a chunk of uranium salt on top. Uranium salts were known to be phosphorescent, and sets the whole thing in the sun. His idea is that sunlight will excite the uranium will phosphoresce, and if X-rays are part of that process, they'll pass through the black paper and fog the photographic plate underneath. He runs the experiment, develops the plate, and sure enough, there's a foggy image where the uranium sat. He thinks he's proven his hypothesis. But then, In late February of 1896, Paris has several overcast days in a row. Becquerel can't run his experiment because there's no sun, so he sticks the whole setup, the wrapped plate with the uranium salt sitting on top, in a drawer, and waits for the weather to clear. Here's where it gets interesting. After a few days, for reasons that aren't entirely clear, maybe impatience, maybe a hunch, maybe just good scientific instinct, he decides to develop the photographic plate anyway, even though it's been sitting in a dark drawer with no sunlight to trigger the phosphorescence. And the image is there, clear as anything. The uranium has fogged the plate all by itself, in total darkness, without any external energy source. Think about what that means. The uranium isn't re-emitting energy it absorbed from the sun. It's producing some kind of radiation on its own, spontaneously, from within. This isn't phosphorescence at all. It's something completely new. Becquerel has just discovered radioactivity, though that word doesn't exist yet. He doesn't fully grasp what he's found. He publishes his results. And honestly, the scientific world is a little underwhelmed. X-rays are the exciting thing. Becquerel's uranium rays seem like a curiosity. But there's a young Polish woman in Paris who is paying very close attention. Her name is Maria Sklodowska, though the world will come to know her as Marie Curie. She's recently married Pierre Curie, a French physicist, and she's looking for a doctoral research topic. Becquerel's uranium rays intrigue her precisely because nobody else seems very interested in them. She sees an open field, and she starts asking a beautifully simple question. Is uranium the only element that does this? She begins systematically testing every element and mineral she can get her hands on. She borrows a sensitive instrument that Pierre and his brother had invented, a piezoelectric electrometer, which can measure tiny electrical charges in the air. Radioactive materials ionize the air around them, knocking electrons loose from air molecules, which makes the air slightly conductive. So she can actually measure the intensity of the radiation by measuring how much current flows through the air near a sample. It's an elegant setup, and she discovers something crucial. She finds that thorium is also radioactive, which tells her this isn't some quirk unique to uranium. It's a property that certain elements have. But then she finds something even more puzzling. When she tests pitchblende, which is the ore that uranium comes from, the radiation she measures is stronger than it should be, stronger than pure uranium alone would produce. That means there's something else in the pitchblende, something more radioactive than uranium itself. So she and Pierre set about trying to isolate it. And this is where the story becomes genuinely heroic in a very physical, unglamorous way. They're working in a converted shed at the School of Physics and Chemistry in Paris. It's drafty, it leaks, it's either freezing or sweltering depending on the season. And they're processing tons, literally tons, of pitchblende ore, boiling it in huge vats, filtering, precipitating, separating, over and over. Marie is often stirring the massive pots herself, for hours. The work is backbreaking, but it pays off. In 1898, they announced the discovery of 2 new elements. The first they name polonium, after Marie's homeland of Poland, which at the time doesn't even exist as an independent country on the map. The second they name radium. And radium turns out to be extraordinarily radioactive, about 1 million times more radioactive than the same amount of uranium. It glows in the dark with an eerie blue-green light. It's warm to the touch from the energy it's releasing. It's mesmerizing, and it's dangerous, though they don't fully understand that yet. Marie Curie will eventually win 2 Nobel Prizes, one in physics, shared with Pierre and Becquerel, and one in chemistry, on her own. She remains the only person ever to win Nobels in 2 different sciences, and the concept she helped define, radioactivity, is the absolute foundation of everything that comes next in our story. Because radioactivity is what happens when an atomic nucleus is unstable. It's trying to reach a more stable configuration, and to do that, it throws off particles and energy. That's what Becquerel's photographic plate was detecting. That's what Marie was measuring in her leaky shed. Now, at this point, around the turn of the 20th century, nobody really understands what an atom looks like inside. They know atoms exist. They know atoms contain electrons, because J.J. Thomson discovered the electron in 1897. But the internal structure is a mystery. Thomson proposes a model. He imagines the atom as a sort of blob of positive charge with electrons embedded in it, like raisins in a pudding. The British actually call this the plum pudding model, which is a wonderfully cozy name for a physics concept. But in 1909, Ernest Rutherford, a New Zealander working in Manchester, England, runs one of the most important experiments in the history of science. He and his colleagues Hans Geiger and Ernest Marsden fire tiny alpha particles, which are basically little chunks of helium nuclei, at a thin sheet of gold foil. If the plum pudding model is right, the alpha particles should mostly pass through with only slight deflections, because the positive charge is spread out evenly, and there's nothing very dense to bounce off of. Most of the alpha particles do pass straight through, but some of them bounce back. Not just deflect, some of them come almost straight back toward the source. Rutherford later says, "It was as if you fired an artillery shell at a piece of tissue paper, and the shell came back and hit you. That result makes no sense under the plum pudding model. The only way to explain it is if almost all the mass and positive charge of the atom is concentrated in a tiny, incredibly dense core." Rutherford has discovered the atomic nucleus. And this is where things start to connect to nuclear power, because once you know there's a nucleus, you can start asking what it's made of and what holds it together. Rutherford identifies the proton, a positively charged particle in the nucleus, by 1919. But there's a problem. The masses of atoms are too heavy to be explained by protons alone. Helium, for example, has 2 protons, but its atomic mass is 4, not 2. Something else is in there, something with mass but no electrical charge. Rutherford suspects this as early as 1920 and even coins the word neutron for this hypothetical particle. But actually finding it takes another 12 years. In 1932, James Chadwick, working in Rutherford's lab at Cambridge, finally pins down the neutron. He does it by analyzing a peculiar type of radiation that other researchers, including Irène Joliot-Curie, Marie's daughter, and her husband Frédéric, had been producing but misidentifying. They'd been bombarding beryllium with alpha particles and getting a strange, penetrating radiation out. The Joliot-Curies thought it was gamma rays. Chadwick showed it was actually a stream of particles with roughly the same mass as protons, but no charge. Neutrons. And here's why the neutron changes everything. Because it has no electrical charge, it isn't repelled by the positively charged nucleus the way a proton or an alpha particle would be. You can fire a neutron at an atom, and it can just waltz right in, no resistance, and slam into the nucleus. That makes neutrons the perfect tool for probing and manipulating atomic nuclei. They're like a skeleton key that can open any atomic door. Now, the stage is set for something extraordinary. Scientists across Europe, in Berlin, Paris, Rome, Copenhagen, Cambridge, are all racing to understand what happens when you start bombarding different elements with neutrons. In Rome, a young Italian physicist named Enrico Fermi is systematically working his way through the periodic table, hitting one element after another with neutrons and cataloging the results. He's methodical, brilliant, and he has a remarkable team around him. They make a surprising discovery. If you slow the neutrons down, they're actually more effective at being absorbed by nuclei. Fast neutrons often zip right past, but slow ones linger near the nucleus long enough to be captured. Fermi's group figures this out almost by accident when they notice that their experiments give different results depending on whether the setup is on a wooden table or a marble one. The hydrogen atoms in the wood are slowing the neutrons down. When Fermi bombards uranium, element 92, the heaviest naturally occurring element, with these slow neutrons, he gets a confusing mess of radioactive products. He thinks he might have created new elements heavier than uranium, elements 93 and 94, which would be a tremendous discovery. He's cautious about the claim, but the press isn't, and soon there's excitement about transuranic elements. He wins the Nobel Prize in 1938, in part for this work. But there's a problem. Over in Berlin, two German chemists, Otto Hahn and Fritz Strassmann, are carefully repeating and extending Fermi's uranium experiments, and they keep finding something that doesn't make sense. Among the products of neutron-bombarded uranium, they're detecting barium. Barium is element 56. It has roughly half the atomic weight of uranium. It shouldn't be there. There's no known process by which bombarding uranium with a single neutron could produce barium. Hahn is an exceptional chemist, meticulous, and he trusts his results, but he can't explain them. So in December 1938, he writes a letter to his longtime collaborator, the Austrian-Swedish physicist Lise Meitner, who had been forced to flee Germany earlier that year because of her Jewish heritage. She's in Sweden now, and it's Christmas, and she's visiting friends in a small town called Kungälv when Hahn's letter arrives. Meitner reads the letter and immediately starts thinking. Her nephew, Otto Robert Frisch, who is also a physicist, happens to be visiting for the holidays. He finds her pacing, agitated, working through the problem. And together, on a walk through the snowy Swedish countryside, Frisch on cross-country skis, Meitner on foot, they work out what's happening. The uranium nucleus, when it absorbs a neutron, isn't just chipping off a small piece. It's splitting roughly in half. The nucleus is behaving like a wobbly liquid drop that, when given just a little extra energy, elongates and pinches apart into two smaller drops. Meitner calculates the energy that would be released using Einstein's famous equation. Energy equals mass times the speed of light squared, and the numbers are staggering. A single uranium atom splitting releases about 200 million electron volts. That's roughly 1,000,000 times more energy than a single chemical reaction, like burning a molecule of coal. Frisch rushes back to Copenhagen and tells Niels Bohr, who is about to board a ship for America. Bohr reportedly slaps his forehead and says something like, "Oh, what fools we've all been." It was obvious in retrospect. Frisch borrows the term fission from biology, where it describes a cell dividing in two, and the word sticks. By January 1939, the news is spreading through the physics community like wildfire. And almost immediately, a critical question arises. A question that will shape the rest of the 20th century and lead, eventually, to every nuclear power plant operating today. When a uranium atom splits, it releases energy, yes. But does it also release extra neutrons? Because if it does, if each fission event kicks out 1 or 2 or 3 neutrons, and those neutrons go on to split other uranium atoms, which release more neutrons, which split more atoms, then you don't just have a single reaction. You have a chain reaction. And a chain reaction means you could release energy on a scale that nobody had ever seriously imagined before. Not a single atom splitting, but billions upon billions of them, each one triggering the next, a cascade of energy building on itself in a fraction of a second. Or, if you could control it, sustained over minutes, hours, days. That's the question hanging in the air in early 1939. And physicists all over the world realize they need to answer it fast. Now, the idea of a chain reaction wasn't brand new. A Hungarian physicist named Leo Szilard had actually been thinking about this concept for years. And Szilard is one of those figures in the history of science who deserves way more attention than he gets. He was brilliant, restless, perpetually worried about the future, and almost eerily prescient. Back in 1933, years before anyone had split a uranium atom, Szilard was walking through London, waiting at a traffic light on Southampton Row, and he had this flash of insight. He'd been reading about Rutherford dismissing the idea that energy could ever be practically extracted from atoms, calling it moonshine, and Szilard thought, well, what if there's an element that, when hit by a neutron, releases 2 neutrons? Then one reaction triggers 2, 2 trigger 4, 4 trigger 8, and so on. An exponential chain. He filed a patent on the idea in 1934, a patent on a nuclear chain reaction, years before fission was even discovered. He actually assigned the patent to the British Admiralty and had it classified, because even then, he was worried about what this could mean if it fell into the wrong hands. That's Szilard for you. Always thinking 3 steps ahead, always anxious about the consequences. So when the news of fission breaks in January 1939, Szilard, who's now living in New York, immediately grasps the implications. He contacts Enrico Fermi, who's also in New York. Fermi had emigrated from Italy just weeks earlier, partly because his wife Laura was Jewish, and Mussolini's racial laws were making life increasingly dangerous. Fermi had actually collected his Nobel Prize in Stockholm in December 1938 and simply never went back to Italy. He took his family straight to New York. So now you have 2 of the most brilliant nuclear physicists in the world, both refugees in a sense, both in the same city, and both asking the same question. Does uranium fission produce extra neutrons? The experiments happen remarkably quickly. Within weeks, multiple groups confirm it. Frédéric Joliot-Curie's team in Paris, and yes, that's the son-in-law of Marie Curie, they measure it. Fermi and his collaborators at Columbia University measure it, and the answer is yes. Each uranium fission event releases, on average, about 2 to 3 neutrons. 2 to 3. That number might sound small, but think about what it means. 1 neutron splits 1 atom, which releases, say, 2.5 neutrons on average. Each of those can split another atom, releasing 2.5 more each. After just 10 generations of this, you've gone from 1 fission event to roughly 10,000. After 20 generations, you're at 10 million. After 80 generations, you've got more fission events than there are atoms in a meaningful chunk of uranium. And each generation happens in a tiny fraction of a second. We're talking nanoseconds. So in theory, you could release an astronomical amount of energy almost instantaneously. But here's the thing. And this is where the physics gets really interesting and really important for understanding how nuclear power actually works. In practice, it's not that simple. Not every neutron that's released actually goes on to split another uranium atom. Neutrons can escape from the material entirely. They can be absorbed by other atoms without causing fission. they can be absorbed by uranium atoms in a way that doesn't cause them to split. Whether or not you actually get a self-sustaining chain reaction depends on a very specific balance. On average, does each fission event lead to at least one more fission event? If yes, the reaction sustains itself. If no, it fizzles out. Physicists call this the criticality condition, and the key number is called K, the multiplication factor. If K equals exactly 1, every fission event leads, on average, to exactly one more fission event. The reaction sustains itself at a steady rate. That's called being critical, and despite how dramatic that word sounds, it's actually exactly what you want in a nuclear reactor. Critical just means self-sustaining and stable. If K is less than 1, the reaction dies out, subcritical. And if K is greater than 1, the reaction is growing, supercritical. In a bomb, you want K to be significantly greater than 1 for as long as possible. In a reactor, you want to hover right around 1, making tiny adjustments to keep things steady. Now, here's a subtlety that turns out to be absolutely crucial. Maybe the single most important lucky break in the entire history of nuclear power. Not all the neutrons from fission are released at the same time. Most of them, more than 99%, come out instantly, within a tiny fraction of a second of the atom splitting. These are called prompt neutrons. But a small fraction, less than 1%, are delayed. They come from the fission products, those two smaller atoms that the uranium split into, and they're emitted seconds or even minutes later as those products undergo their own radioactive decay. These are called delayed neutrons, and they might seem insignificant, but they change everything. Here's why. If you had to control a chain reaction that depended only on prompt neutrons, you'd be trying to manage something where each generation happens in about 100 millionth of a second. The reaction could go from stable to doubling every microsecond before you could even blink, let alone move a control rod. It would be essentially impossible to control mechanically. But because of that small fraction of delayed neutrons, the effective time between generations stretches out to something more like 1/10 of a second, or even longer. And that's a timescale that humans and machines can work with. You can design control systems that respond fast enough. You can make adjustments. You can keep K hovering right at 1. So let that sink in for a moment. The reason we can build nuclear power plants at all, the reason nuclear energy can be a controlled, steady source of electricity rather than only an uncontrollable explosion, is because less than 1% of fission neutrons happen to be delayed by a few seconds. If the physics had worked out just slightly differently, if all neutrons were prompt, controlled nuclear power might have been effectively impossible. It's one of those beautiful accidents of nature that makes the whole thing work. But in 1939, people aren't thinking much about power plants yet. The world is sliding toward war, and the physicists who understand what a chain reaction means are terrified. Szilard, in particular, is consumed with dread. He knows that German scientists discovered fission. He knows that Germany has access to uranium from Czechoslovakia, which it has just occupied. And he knows that if the Germans figure out how to build a bomb first, the consequences would be unthinkable. So Szilard does something remarkable. He convinces Albert Einstein, the most famous scientist in the world, to sign a letter to President Franklin Roosevelt, warning him that a new type of extremely powerful bomb might be possible, and urging the United States to begin its own research. The letter is dated August 2nd, 1939, exactly 1 month before Germany invades Poland and World War II begins. Einstein later called signing that letter the greatest mistake of his life, but at the time, The fear of Nazi Germany getting the bomb first made it feel necessary. Roosevelt receives the letter and sets up an advisory committee, but progress is slow at first. The real urgency doesn't kick in until 1941, when a British report called the Maud Committee Report concludes that an atomic bomb is not only possible, but could be built within a few years using a specific form of uranium. Uranium-235. And this is where we need to talk about isotopes for a moment, because this distinction between uranium-235 and uranium-238 is absolutely fundamental to understanding nuclear power, and it trips people up all the time. So here's the deal. Uranium, as you find it in nature, is mostly one type. Uranium-238. About 99.3% of natural uranium is U-238. Only about 0.7% is U-235. Same element, same number of protons, 92, but U-235 has 3 fewer neutrons in its nucleus. That's what makes it a different isotope. Same chemical behavior, almost the same mass, but very different nuclear behavior. And the critical difference is this: U-235 is fissile. When a slow-moving neutron hits it, it readily splits apart, releasing energy and more neutrons. U-238, on the other hand, is much more stubborn. It can absorb neutrons, but it usually doesn't fission from slow neutrons. It just swallows them up. In fact, U-238 is so good at absorbing neutrons without fissioning that it actually works against a chain reaction in many scenarios. It's capturing neutrons that could otherwise be splitting U-235 atoms. This creates an enormous practical problem. The stuff that actually sustains a chain reaction, U-235, makes up less than 1% of natural uranium, and separating U-235 from U-238 is fantastically difficult because they're chemically identical. You can't use any chemical process to pull them apart. The only difference is a tiny variation in mass, 3 neutrons worth out of 235 or 238. That's a mass difference of about 1%. Imagine trying to sort 2 piles of nearly identical marbles where one pile's marbles are 1% heavier than the others. At the atomic scale. This separation problem, what's called enrichment, became one of the most massive industrial challenges of the entire Manhattan Project. Entire cities were built to do it. Oak Ridge, Tennessee, which didn't even exist before 1942, was constructed in secret and at its peak employed over 75,000 people, most of whom had no idea what they were actually making. They used multiple enrichment methods simultaneously: gaseous diffusion, electromagnetic separation, thermal diffusion. Each one a colossal engineering undertaking on its own. The gaseous diffusion plant alone was the largest building in the world at the time, covering acres and acres, filled with thousands of barriers through which uranium hexafluoride gas was pushed, stage after stage, each one slightly increasing the concentration of U-235. Thousands of stages to go from that natural 0.7% up to the 90+% needed for a weapon. But while the enrichment effort was consuming unimaginable resources, there was a parallel track. And this is where we come back to Enrico Fermi and a squash court underneath the football stadium at the University of Chicago. Because before you can build a bomb or a power plant or anything else, you need to prove that a self-sustaining chain reaction is actually possible in practice, not just in theory. And that's exactly what Fermi set out to do. He was going to build the world's first nuclear reactor, though they didn't call it that yet. They called it a pile. Literally, because that's what it was. A carefully constructed pile of uranium and graphite stacked up in layers, block by block, in a space that had once been used for racquetball and squash games. Not exactly the kind of place you'd expect to find the most important physics experiment in history. So picture this. It's the fall of 1942. Fermi and his team, a mix of physicists, graduate students, and technicians, are working in this underground space beneath the west stands of Stagg Field. The room is about 60 feet long, maybe half as wide, with a ceiling that's just barely high enough for what they're building. And what they're building is, well, a pile. That's really the best word for it. They're stacking blocks of graphite, purified carbon, in layers, with lumps of uranium and uranium oxide embedded at precise intervals throughout. The graphite is the moderator, the thing that slows neutrons down so they're more likely to cause fission in the uranium. And the uranium, of course, is the fuel. Every layer they add, the pile gets a little closer to that magic number, K equals 1, where the chain reaction sustains itself. Now, here's something you should know about the conditions they were working in. Graphite is messy. It's basically a form of carbon, and when you machine it into blocks and stack thousands of them, the dust gets everywhere. These physicists looked like coal miners by the end of each day. Their skin was gray, their clothes were gray, the floor was gray. They were working long shifts, sometimes around the clock, because there was a war on, and everyone felt the urgency. And they were doing this in the middle of a major American city, under a football stadium, with no radiation shielding to speak of, and no containment structure. If something went wrong, if the reaction got away from them, there was no backup plan that would protect Chicago. Fermi was simply that confident in his calculations. And honestly, he had reason to be. Fermi was one of those rare physicists who was brilliant at both theory and experiment. He could derive the equations, and he could build the apparatus. His colleagues used to joke that Fermi was the last physicist who knew all of physics. So when Fermi said the pile would behave, people believed him. But still, underneath a football stadium in Chicago, the pile grew day by day. They started in early November 1942, and as each new layer went on, they measured the neutron activity inside. Fermi had this methodical approach. He'd calculate in advance what the neutron multiplication should be at each stage, and then they'd measure it, and his predictions kept matching reality with eerie precision. They had cadmium control rods, strips of cadmium, which is a fantastic neutron absorber, inserted into the pile. As long as the cadmium rods were in, they soaked up enough neutrons to keep K below 1. The idea was simple. Build the pile big enough that it would go critical if the rods were pulled out, but keep the rods in until you're ready. And they also had a safety rod. They called it ZIP, which stood for something like Zone of Immediate Precipitation. Though, honestly, the acronym was a bit of a joke. This was a rod that was held in place by a rope, and if anything went wrong, someone would cut the rope with an axe, and the rod would drop into the pile by gravity, shutting the reaction down. That person, Norman Hilberry, literally stood there with an axe during the critical experiment, which is both reassuring and slightly terrifying. They also had what they called the Suicide Squad. This was a group of 3 young physicists standing on a platform above the pile, holding buckets of cadmium sulfate solution. If everything else failed, if the control rods didn't work, if ZIP didn't drop, these guys were supposed to pour the liquid cadmium over the pile to flood it and absorb the neutrons. That was the last line of defense. Buckets, held by hand, on a platform above an active nuclear reactor. December 2nd, 1942. That's the date. It was a Wednesday, and it was cold in Chicago. Early December cold, the kind where your breath hangs in the air. About 40 people gathered in the squash court that morning, standing on a balcony overlooking the pile. Fermi was calm, methodical, almost serene. He directed the control rods to be withdrawn in stages, a few inches at a time. After each withdrawal, he'd wait, watch the instruments, check the neutron counts against his calculations, and then nod for the next step. The clicking of the neutron counters got faster. The pen on the chart recorder climbed. At one point around lunchtime, Fermi actually called a break. He told everyone to go eat. The pile was close to critical. The tension in the room was palpable, and Fermi said, "Let's have lunch." That's the kind of person he was. Cool under pressure in a way that almost defied belief. After lunch, they resumed. More rod withdrawal. The counters clicked faster and faster. And then, at 3:25 in the afternoon, Fermi gave the order for the last rod to be pulled out another foot. The neutron intensity began to rise, not to a peak and then level off, but to rise and keep rising. Exponentially. That's the signature of a self-sustaining chain reaction. K had crossed 1. The pile was critical. Fermi watched the instruments with a small smile on his face, let it run for about 4.5 minutes, and then ordered the control rods reinserted. The counters slowed. The reaction stopped. And that was it. The nuclear age had begun, right there, in a squash court in Chicago. Arthur Compton, who was overseeing the project, made a famous phone call to James Conant at Harvard. He said, "The Italian navigator has landed in the New World." Conant asked, "How are the natives?" And Compton replied, "Very friendly." That was the coded message confirming that the first self-sustaining nuclear chain reaction had been achieved. The Italian navigator, of course, was Fermi. Now here's what I want you to appreciate about what had just happened, because it's easy to rush past it. The pile produced about 1/2 a watt of power. 1/2 a watt. That's less than a flashlight. It wasn't useful for anything in a practical sense. But what it proved was enormous. It proved that a controlled, self-sustaining chain reaction was real. Not theoretical, not hypothetical, but physically demonstrated. And it proved something else, something that matters deeply for our story about nuclear power. It proved that you could control it. Those delayed neutrons we talked about earlier, that tiny fraction of neutrons that come out a few seconds late, they were doing their job. The pile responded slowly enough that a human being could manage it with control rods. Fermi could nudge the reaction up, hold it steady, bring it back down. The reactor was tame. It was obedient. And that obedience is the entire foundation of nuclear power as an energy source. Without it, you'd have something that either fizzles out or runs away from you, and neither of those is useful for generating electricity. But Fermi's pile wasn't built to generate electricity. It was built to prove a concept, and also, and this is important, to produce plutonium. See, here's something that had been figured out theoretically by this point. When uranium-238 absorbs a neutron but doesn't fission, it doesn't just sit there. It undergoes a series of radioactive decays. First it becomes neptunium-239, and then that decays into plutonium-239. And plutonium-239, it turns out, is fissile. It splits when hit by a neutron, just like U-235 does, which means you've just created a new nuclear fuel out of the abundant, otherwise mostly useless U-238. Think about what that means. You don't have to painstakingly separate the rare U-235 from the common U-238. You can instead build a reactor, run it with natural or slightly enriched uranium, and the reactor itself will transmute some of that U-238 into plutonium, which you can then extract chemically. Chemical separation is vastly easier than isotope separation because plutonium is a different element from uranium, not just a different isotope. Different elements have different chemistry. You can dissolve the fuel, run it through chemical processes, and pull the plutonium out. This was a huge deal for the Manhattan Project because it offered a second path to a bomb, one that didn't require the nightmarish enrichment process at Oak Ridge. And this is exactly what happened next. The success of CP1 led directly to the construction of much larger production reactors at a brand new secret site, Hanford, Washington. If Oak Ridge was the secret city for enrichment, Hanford was the secret city for plutonium production. And the engineering challenges at Hanford were staggering in their own right. The man tasked with designing and building the Hanford reactors was DuPont. Yes, the chemical company. The Army Corps of Engineers under General Leslie Groves contracted DuPont to scale up Fermi's squash court experiment by a factor of millions. CP1 had operated at half a watt. The Hanford B reactor, the first of the production reactors, was designed to operate at 250 megawatts. That's not a typo. From half a watt to 250 million watts. And they had to design and build it in roughly a year, with a process that had never been done before, producing a material, plutonium, that existed only in microgram quantities on Earth. The B reactor went critical on September 26, 1944, and almost immediately, something went wrong. The reactor started up fine, reached its design power level, and then the power began to drop. Slowly at first, then faster. Within hours, the reactor had shut itself down. Nobody had predicted this. Fermi was baffled. Enrico Fermi, who was almost never baffled, didn't know what was happening. Here's what was going on. And this is one of those beautiful stories where a cautious engineering decision made months earlier ended up saving the entire project. When the reactor was being designed, the physicists calculated that they needed about 1,500 fuel channels, tubes running through the graphite core where the uranium fuel slugs would sit. DuPont's engineers, led by a man named John Wheeler and working closely with the company's own engineering culture, insisted on adding extra tubes. They pushed for 2,004 tubes instead of 1,500. The physicists thought this was overkill, a waste of resources. There was real friction about it, but DuPont had a long history of scaling up chemical processes, and they knew from hard experience that when you're doing something for the first time at industrial scale, you build in margin. You always build in margin. So the extra tubes went in. And thank goodness they did, because what was poisoning the reactor was xenon-135, a fission product, one of the fragments left over when a uranium atom splits. Xenon-135 turns out to be the most powerful neutron absorber ever discovered. It has an absolutely enormous appetite for neutrons, thousands of times greater than cadmium or boron. As the reactor ran, fission products accumulated, and xenon-135 built up in the fuel. It gobbled up so many neutrons that K dropped below 1, and the reaction died. Nobody had accounted for this because xenon-135 is also radioactive. It decays away with a half-life of about 9 hours. So if you waited long enough after shutdown, the xenon would decay, and the reactor would be able to start up again. Which is exactly what happened. The reactor came back to life on its own after several hours, confirming the diagnosis. But here's the thing. You can't run a production reactor that keeps shutting itself down every few hours. You need to overpower the xenon, to have enough excess reactivity to keep the chain reaction going, even with all that xenon-135 soaking up neutrons. And that's where DuPont's extra 500 tubes saved everything. By loading uranium into those additional channels, they could boost the reactor's reactivity enough to overwhelm the xenon poisoning and run continuously. If they'd built only 1,500 tubes as the physicists originally specified, the Hanford B reactor would have been a very expensive paperweight. The plutonium production timeline would have been set back by months, maybe longer, with enormous consequences for the war effort. John Wheeler later called it the most important engineering decision of the project. And it's a perfect example of something you see over and over in nuclear engineering: the interplay between pure physics and practical engineering judgment. The physicists understood fission, they understood neutron multiplication, they could calculate criticality. But they didn't know about xenon-135 poisoning because it had never been observed before. The DuPont engineers didn't know about it either, but they knew that unknown unknowns exist, and they built in margin to handle them. That instinct, that deeply ingrained habit of leaving room for what you don't know, is one of the most important ideas in all of engineering, and in nuclear engineering, it becomes absolutely foundational. Because when you're dealing with a technology where the consequences of getting it wrong are measured in contaminated landscapes and human lives, margin isn't a luxury. It's a moral obligation. And that principle, building in room for what you haven't imagined yet, shaped everything that came after Hanford. It shaped the way reactors were designed, the way they were operated, and eventually, the way they were regulated. But we're getting a little ahead of ourselves. Because before nuclear energy could become anything resembling a civilian technology, before anyone was seriously thinking about generating electricity for homes and businesses, there was still a war to finish, and the reactors at Hanford did finish their part of that job. By early 1945, Hanford was producing plutonium at a steady rate, and that plutonium was shipped to Los Alamos, New Mexico, where it was fashioned into the core of the Fat Man bomb, the weapon that was dropped on Nagasaki on August 9, 1945. The other bomb, Little Boy, dropped on Hiroshima 3 days earlier, used uranium-235 that had been painstakingly separated at Oak Ridge. 2 bombs, 2 paths to fissile material, both of which required reactors or enrichment facilities of staggering scale. And then the war ended. Now, here's where the story shifts in a really profound way. Because suddenly, you have this technology, this incredibly powerful, deeply understood, massively funded technology. And the war it was built for is over. What do you do with it? You have thousands of scientists and engineers who now understand nuclear fission better than anyone in history. You have industrial infrastructure. You have a government that has spent the equivalent of roughly $30 billion in today's money on the Manhattan Project. And you have this tantalizing fact sitting right in front of everyone. A single kilogram of uranium-235 fully fissioned releases energy equivalent to about 20,000 tons of coal. 20,000 tons. Think about that. A lump of metal you could hold in one hand, and it contains the same energy as a trainload of coal stretching for miles. The energy density of nuclear fuel is almost incomprehensibly large compared to chemical fuels, and people noticed. Even during the war, some of the Manhattan Project scientists had been thinking about peacetime applications. Enrico Fermi talked about it. So did many others. The idea of using nuclear fission to generate electricity was obvious in principle. You have a source of enormous heat, and we already knew how to turn heat into electricity. That's what every coal plant and every oil plant does. You burn fuel, you make heat, you boil water into steam, the steam spins a turbine, the turbine spins a generator, and out comes electricity. The nuclear version just replaces the furnace with a reactor. Instead of burning coal, you sustain a controlled chain reaction, and the kinetic energy of those fission fragments, remember, those two pieces of the split atom flying apart at tremendous speed, gets converted to heat as they slam into surrounding material. That heat gets carried away by a coolant, usually water, and from there it's the same story. Steam, turbine, generator, electricity. Simple in concept, incredibly complex in practice. And the journey from concept to working power plant is one of the great engineering stories of the 20th century. But first, there was a political question to settle, and it was a big one. Who would control this technology? The military had built it, the military had used it, and the military wanted to keep it. But a lot of the scientists who had worked on the bomb were deeply uncomfortable with that idea. They'd seen what the technology could do, and many of them, Leo Szilard prominent among them, argued passionately that nuclear energy should be under civilian control. There was a fierce debate in Congress through 1945 and 1946, and it resulted in the Atomic Energy Act of 1946, which created the Atomic Energy Commission, or AEC. And here's what's significant. The AEC was a civilian agency, not military. It took control of all nuclear materials, all nuclear facilities, all nuclear research in the United States. The military could request weapons, but it couldn't build them on its own. This was a remarkable decision, when you think about it. In the immediate aftermath of a war won partly through nuclear weapons, the United States chose to put this technology under civilian authority. And the AEC had a dual mandate: to continue weapons development, yes, but also to explore and promote peaceful uses of atomic energy. That second part of the mandate is what opens the door to everything we're going to talk about now. The first person who really needs to enter our story at this point is a naval officer named Hyman Rickover. And if you know anything about nuclear power, you've probably heard his name, because Rickover is arguably the single most important figure in the development of practical nuclear energy. Not the physics, Fermi and the others had that covered, but the engineering. The actual, working, reliable, don't-blow-up engineering of nuclear reactors. That was Rickover's domain, and he pursued it with a ferocity that is honestly hard to overstate. Rickover was born in 1900 in what is now Poland, came to the United States as a child, and eventually made it to the Naval Academy. He was not popular there. He was short, intense, abrasive, and Jewish in an institution that was none of those things by preference. He graduated in 1922 and spent the next 2 decades working his way through various naval engineering assignments, eventually specializing in electrical engineering and submarine propulsion. He was brilliant, demanding, and almost pathologically detail-oriented, the kind of person who would read every technical report himself, who would call an engineer at 2 a.m. to ask about a valve specification, who would personally interview every single officer assigned to his program. People either respected him enormously or despised him, often both at the same time. In 1946, the Navy sent Rickover and a small group of officers to Oak Ridge to learn about nuclear technology, and Rickover immediately saw the possibility that would define the rest of his career: a nuclear-powered submarine. Think about why this matters. Conventional submarines in World War II ran on diesel engines on the surface and electric batteries when submerged. The batteries had limited capacity. A sub could only stay underwater for a day or two at slow speed before it had to surface and run its diesel engines to recharge. That made submarines vulnerable. They had to come up for air, essentially. A nuclear reactor doesn't need air. It doesn't burn anything. It doesn't consume oxygen. A nuclear-powered submarine could stay submerged for weeks, months even, limited only by the crew's food supply and psychological endurance. It would be a true submarine, not a surface ship that could occasionally dive, which is really what World War II subs were. This was a transformative military concept, and Rickover grabbed onto it with both hands and refused to let go. Now, here's where the engineering gets really interesting, because Rickover had to solve a problem that nobody had solved before. He needed a reactor that was compact enough to fit inside a submarine hull, reliable enough to operate at sea for years, safe enough that you could put a crew of 100 men right next to it, and powerful enough to drive a submarine at high speed underwater. And he needed it to actually work, not in theory, not as an experiment, but as a deployable military system. This was a completely different challenge from anything that had come before. The Hanford reactors were enormous, building-sized structures with thousands of fuel channels surrounded by massive concrete shielding, operated by large teams of technicians. You couldn't put anything like that in a submarine. Rickover made a critical early decision that shaped the entire future of nuclear power, and it's worth understanding why. He chose to use pressurized water as both the coolant and the moderator for his submarine reactor. Let me explain what that means and why it mattered. You need a moderator, remember, to slow down the fast neutrons from fission so they can cause more fissions in uranium-235. In Fermi's Chicago pile, the moderator was graphite, solid blocks of carbon. At Hanford, same thing, graphite. But graphite reactors are bulky. You need a lot of graphite to moderate enough neutrons, and that means a big reactor. Water, it turns out, is also a pretty good moderator. Hydrogen atoms in water are almost the same mass as neutrons, which means when a neutron collides with a hydrogen atom, it transfers a lot of its energy, like a billiard ball hitting another billiard ball of the same size. Very efficient at slowing neutrons down. And water has another obvious advantage. It can also carry heat away from the reactor core, so you can use the same substance as both your moderator and your coolant. That's elegant. That's compact. That's what you want in a submarine. But there's a catch, and it's a significant one. If you let water boil inside the reactor, if it turns to steam right there in the core, you lose your moderator, because steam is much less dense than liquid water, so it's much worse at slowing down neutrons. Losing your moderator means fewer fissions, which means less power, which could mean losing control of the reactor in complicated ways. So Rickover's team decided to keep the water in the reactor core under very high pressure, high enough that it couldn't boil even at temperatures well above water's normal boiling point. At around 155 atmospheres of pressure, water stays liquid up to about 345 degrees Celsius. So you have this incredibly hot water, way hotter than boiling at normal pressure, but it's still liquid because you're squeezing it so hard. This hot, pressurized water flows through the reactor core, picks up heat from the fuel, and then passes through a device called a steam generator, basically a big heat exchanger where the hot pressurized water from the reactor transfers its heat to a separate loop of water that's at lower pressure. That second loop of water boils into steam, and that steam drives the turbines. The key insight is that the radioactive water from the reactor never directly touches the turbines. It stays in its own sealed loop. The steam that drives the turbines comes from a separate, clean water supply. 2 loops. The primary loop is radioactive and under enormous pressure. The secondary loop is clean and produces the working steam. This is the pressurized water reactor, the PWR, and it became the dominant reactor type in the world. Not because it's necessarily the best design in every way, but because Rickover built it first, proved it worked, and created an entire industrial infrastructure around it. The project moved fast by any standard. Rickover established the Naval Reactors branch in 1949 and partnered with Westinghouse Electric Corporation to design and build the reactor. They constructed a land-based prototype in the Idaho desert. A full-scale reactor plant built inside a submarine hull section, sitting on dry land, so they could test everything before putting it in an actual boat. This prototype, called S1W, achieved criticality in March 1953. And then the real thing, USS Nautilus, hull number SSN 571, was launched in January 1954 and commissioned in September of that year. On January 17, 1955, the Nautilus sent the famous message, "Underway on nuclear power." It was the first nuclear-powered vessel in history, and it worked beautifully. The Nautilus shattered every submarine record. In 1958, it made the first submerged transit under the North Pole, traveling beneath the Arctic ice cap, something no diesel submarine could have dreamed of attempting. The reactor ran and ran and ran. Rickover's obsessive attention to quality, his insistence on testing everything, his refusal to accept shortcuts, it all paid off. The Navy's nuclear propulsion program has operated for over 60 years now, with an extraordinary safety record. And the reason I'm spending so much time on Rickover and submarines is that the pressurized water reactor he developed didn't stay in submarines. It came ashore. Because when the United States decided to build its first commercial nuclear power plant, the people involved looked around for a proven reactor design, and there was really only one that had been built, tested, and operated successfully at significant power levels: Rickover's PWR. The Westinghouse engineers who had built the submarine reactor knew how to build pressurized water reactors. The supply chains existed. The expertise existed. And so, the first major civilian nuclear power plant in the United States, Shippingport Atomic Power Station in Pennsylvania, was essentially a scaled-up version of a submarine reactor. It went critical in December 1957 and began delivering electricity to the grid. Rickover personally oversaw the project. And this is one of those moments in engineering history where a decision made for very practical, very specific reasons, we need a compact reactor for a submarine, ends up shaping an entire global industry for decades. Because once Shippingport proved that a PWR could generate civilian electricity, and once Westinghouse started marketing the design to utilities, the PWR became the template. Today, roughly 2/3 of all operating nuclear power plants in the world are pressurized water reactors. The other major type, the boiling water reactor, or BWR, is closely related. It also uses water as coolant and moderator, but it lets the water actually boil in the core, which simplifies the design by eliminating the steam generator but introduces other complications. General Electric developed the BWR as a competitor to Westinghouse's PWR, and between the two of them, light water reactors, reactors that use ordinary water, dominate the global fleet. And it all traces back to Rickover needing something that would fit inside a submarine. But here's the thing that's worth sitting with for a moment. The PWR wasn't chosen for civilian power because it was the optimal design for generating electricity. It was chosen because it existed, because it was proven, because there were people who knew how to build it. There were other reactor concepts, some of them arguably better suited for civilian power generation, that got less attention, less funding, less development, because the PWR had a head start. And some of those alternative designs are now being revisited 70 years later by a new generation of engineers who are asking whether we made the right choice. We'll get into some of those alternatives later. But first, I want to talk about what happened when nuclear power went commercial in a big way, because the 1960s were a remarkable decade for the nuclear industry. Really remarkable, because in the span of about 10 years, nuclear power went from a handful of demonstration plants to a massive commercial enterprise with dozens of reactors ordered, billions of dollars committed, and a genuine belief shared by government officials, utility executives, and a good portion of the public that nuclear energy was going to transform civilization. And to understand how that happened so fast, you have to understand the economics, or at least what people thought the economics were going to be. See, in the late 1950s and early 1960s, the Atomic Energy Commission was actively promoting civilian nuclear power. That was part of its mandate. Atoms for Peace, Eisenhower's vision, the idea that this terrifying technology could be redeemed by turning it toward peaceful purposes. And the AEC did something that, in retrospect, had enormous consequences. It subsidized the early demonstration plants heavily. It provided the enriched uranium fuel. It funded research. It shared technical knowledge that had been developed in the weapons program. And it created an environment where utilities could dip their toes into nuclear power without bearing the full financial risk. Shippingport, which we just talked about, was a prime example. The AEC paid for the reactor itself. Duquesne Light Company paid for the conventional parts of the plant. The turbines, the generators, the electrical infrastructure. It was a partnership designed to prove the concept. And it worked, in the sense that Shippingport operated and fed electricity into the grid. But it was small, only about 60 megawatts of electrical output. That's tiny by later standards. And the electricity it produced was expensive. Much more expensive than coal-fired power at the time. So the question became, could nuclear power be scaled up to the point where it was economically competitive? Could you build reactors big enough and operate them efficiently enough that the cost per kilowatt hour would match or beat fossil fuels? And here's where a very specific phrase enters the story, one that became almost a mantra in the nuclear industry. Too cheap to meter. You've probably heard that phrase. It's often attributed to Lewis Strauss, who was chairman of the AEC, and he said it in a speech in 1954. Now, there's some debate about whether Strauss was actually talking about fission reactors or about the even more speculative prospect of fusion power. But regardless of what he meant, the phrase took on a life of its own. It captured a mood, an expectation, a hope, that nuclear energy would be so abundant and so inexpensive that it would fundamentally change the economics of everything. And that hope, even if it was never quite realistic, drove a lot of the early enthusiasm. By the early 1960s, reactor designs were getting bigger. The first generation of commercial plants, people sometimes call them Generation 1, were relatively small and experimental. But the industry was already pushing toward Generation 2, which would be the workhorses, the large standardized designs that would form the backbone of the nuclear fleet for decades. And the key moment, the one that really kicked off the commercial boom, came in December 1963, when Jersey Central Power and Light Company announced that it was going to build a nuclear plant at Oyster Creek, New Jersey. And here's what made Oyster Creek special. It was ordered on a purely economic basis, not as a demonstration project, not with heavy government subsidies, but because General Electric offered to build it as a turnkey plant, meaning GE would deliver the whole thing, ready to operate for a fixed price, and that price was competitive with a coal plant of similar size. Now, whether GE actually made money on that deal is another question. Most analysts believe GE took a significant loss on Oyster Creek, essentially using it as a loss leader to break into the market. But the signal it sent was enormous. It told every utility executive in the country that nuclear power had arrived as a commercial technology. And the orders started flooding in. Between 1965 and 1967, American utilities ordered more than 50 nuclear power plants. 50. In 3 years. Think about what that means. Each one of these is a massive construction project, a billion-dollar commitment in today's money, a decade-long undertaking from order to operation, and they were being ordered at a pace that the industry could barely keep up with. Westinghouse was selling PWRs, GE was selling BWRs, and the competition between them was fierce. They were offering turnkey contracts, fixed-price deals, essentially betting that they could build these plants cheaply enough to make a profit, and in many cases, they couldn't. Both companies lost money on their early turnkey contracts, but the market momentum was unstoppable. This period is sometimes called the Great Bandwagon Market, and that name tells you something about the psychology involved. Utility executives saw their competitors ordering nuclear plants and felt they couldn't afford to be left behind. There was a genuine fear of being stuck with expensive coal plants while your rival was generating cheap nuclear electricity, and the AEC was encouraging all of it, projecting that the United States would have 1,000 nuclear reactors by the year 2000. 1,000. We ended up with about 104 at the peak. So the projections were wildly optimistic. But let's slow down and talk about what was actually being built, because the engineering matters. These Generation 2 plants were substantially larger than anything that had come before. Oyster Creek was rated at about 640 megawatts electric. By the early 1970s, plants were being designed at over 1,000 megawatts, more than 15 times the output of Shippingport. And scaling up a nuclear reactor is not like scaling up a factory. It introduces engineering challenges at every level. Start with the reactor vessel itself. In a PWR, you've got this massive steel pressure vessel, maybe 40 feet tall, with walls 8 to 12 inches thick, designed to contain water at over 2,000 pounds per square inch and temperatures above 600 degrees Fahrenheit. The vessel has to be manufactured to extraordinary standards, every weld inspected, every inch of steel tested for flaws, because a failure of the pressure vessel is essentially unrecoverable. There's no backup for the vessel. It is the primary barrier between the nuclear fuel and the rest of the plant. And as reactors got bigger, these vessels got bigger, which meant fewer manufacturers in the world could actually make them. The forgings required, massive single pieces of steel, pushed the limits of what the metallurgical industry could produce. Then there's the containment building, that big concrete dome you see in pictures. That's the last line of defense, the structure designed to keep radioactive material from escaping into the environment if everything else goes wrong. These containment structures were being designed to withstand internal pressures from a major accident, external impacts, earthquakes, tornadoes. The amount of reinforced concrete and steel that goes into a containment building is staggering, and every plant had to be designed for the specific geology and seismology of its site, which meant you couldn't just stamp out identical plants. Each one needed site-specific engineering. And here's where the story gets complicated, because all of this was happening against a backdrop of increasing public concern about nuclear safety. The early 1960s were a relatively optimistic time for nuclear power, but by the late 1960s and into the 1970s, questions were being raised. What happens if the cooling system fails? What happens if the fuel melts? What are the consequences of a worst-case accident? These weren't hypothetical questions. The AEC's own advisory committees had been wrestling with them since the 1950s. A landmark report called WASH 740, published in 1957, had tried to estimate the consequences of a major reactor accident near a city, and the numbers were sobering. Thousands of potential casualties, billions of dollars in property damage. The report was meant to inform policy, but it also scared people. And when the AEC tried to update it in the mid-1960s, the revised estimates were even worse, because the reactors being planned were so much larger. The updated report was never officially published. It was suppressed essentially because the AEC worried about the public reaction, and when that suppression eventually came to light, it damaged the AEC's credibility enormously. This is one of the deep tensions in the story of nuclear power, and it's worth sitting with. The AEC had a dual mandate: promote nuclear energy and regulate it for safety. Think about that conflict. The same agency that was cheerleading the construction of nuclear plants was also supposed to be the impartial referee ensuring those plants were safe. And over time, that conflict became untenable. Critics argued, with considerable justification, that the promotional mission was compromising the safety mission, that concerns were being downplayed, that inconvenient findings were being buried, that the regulatory process was too cozy with the industry it was supposed to oversee. This tension would eventually lead to a major institutional change. In 1974, the AEC was abolished, and its functions were split between two new agencies: the Energy Research and Development Administration, which later became part of the Department of Energy, and the Nuclear Regulatory Commission, or NRC, which took over the safety and licensing functions. The separation was meant to resolve the conflict of interest. The NRC would regulate, it wouldn't promote. And that split matters to this day. The NRC remains the primary nuclear safety regulator in the United States, and its independence from the industry is considered foundational. But we're getting a little ahead of ourselves. Let's go back to those plants being built in the late 1960s and early 1970s, because something was happening on the construction side that would have enormous consequences. The plants were taking longer to build than anyone had projected, and they were costing far more than anyone had budgeted. And the reasons were a tangle of engineering challenges, regulatory changes, quality control problems, and, this is important, a learning process that was happening in real time. See, when you're building something as complex as a nuclear power plant, and you're building dozens of them simultaneously, and the designs are still evolving, and the regulations are still being written, you get a situation where changes are being made midstream. A plant that broke ground in 1968 might face new safety requirements in 1971 that required redesigning systems that were already partially built. Pipes that were already installed might need to be rerouted. Walls that were already poured might need additional reinforcement. These backfits, as they're called, added enormous cost and delay. And every delay added more cost, because you're paying interest on billions of dollars of construction loans while the plant sits there generating no revenue. The construction workforce was another challenge. Building a nuclear plant requires an extraordinary level of quality in every weld, every concrete pour, every electrical connection. The standards are far beyond conventional construction. and training enough skilled workers to meet those standards across dozens of simultaneous construction sites stretched the available labor pool thin. Quality control problems were common. Welds that failed inspection had to be cut out and redone. Concrete that didn't meet specifications had to be demolished and repoured. Each deficiency meant more time, more money, more frustration. And then there was something that doesn't get talked about enough: the sheer complexity of these plants. A large nuclear power plant contains something like 30 to 40 miles of piping, miles of electrical cable, thousands of valves, hundreds of pumps, and control systems of staggering intricacy. Every safety-related component has to be traceable. You have to be able to document where the steel came from, who welded it, who inspected the weld, what the test results were. The paperwork alone is a massive undertaking, and this documentation isn't bureaucratic overhead. It's essential, because if something goes wrong 20 years later, you need to be able to trace back and understand exactly what was built and how. So by the mid-1970s, the nuclear industry was in a strange position. There were dozens of plants under construction, many of them running years behind schedule and billions over budget. The utilities that had ordered them were facing financial strain. The public was growing more skeptical. Environmental groups were organizing opposition. And the regulatory framework was tightening, which was necessary for safety, but added yet more cost and complexity. And then, on March 28, 1979, something happened at a nuclear plant in Pennsylvania that would change the trajectory of the entire industry. Unit 2 of the 3 Mile Island Nuclear Generating Station, a pressurized water reactor that had only been operating commercially for about 3 months, experienced a partial meltdown. And to understand what happened there and why it mattered so much, we need to talk about what actually goes wrong when a reactor loses cooling, because that's the heart of the danger with any nuclear reactor. See, when we talked earlier about how a reactor works, the fuel, the chain reaction, the water carrying heat away, there's a detail that makes nuclear power fundamentally different from, say, a coal plant or a gas turbine. And it's this: even after you shut the reactor down, even after you slam every control rod into the core and stop the chain reaction completely, the fuel keeps producing heat. Not a little heat, a lot of heat. And this is the thing that makes nuclear safety so challenging, so unforgiving. Here's why. When uranium atoms split, the fragments they leave behind, the fission products, are themselves radioactive. They're unstable isotopes of things like iodine, cesium, strontium, xenon, dozens of different elements. And these fission products are constantly decaying, releasing energy as they do. This is called decay heat, and you can't turn it off. You can't flip a switch. It's baked into the physics. The moment you shut down a big reactor that's been running at full power, the decay heat is something like 6 or 7% of the reactor's full thermal output. Now, that might sound small, 6%, but think about what that means for a reactor that was producing, say, 3,000 megawatts of thermal energy. 6% of that is 180 megawatts. That's 180 million watts of heat, just from radioactive decay, with no chain reaction happening at all. That's enough to power a small city, and it's all concentrated in a reactor core that's maybe 12 feet across. And the decay heat doesn't just stop. It tapers off, following a curve, dropping relatively quickly at first, then more and more slowly. After an hour, it's down to maybe 1.5% of full power. After a day, maybe 0.5%. But 0.5% of 3,000 megawatts is still 15 megawatts. And that's still an enormous amount of heat being generated inside a sealed vessel. If you don't keep removing that heat, If you lose your cooling water, the fuel starts to heat up, and it heats up fast. The zirconium cladding around the fuel pellets, those thin metal tubes we talked about, they start to fail at temperatures around 2000 degrees Fahrenheit. And if they get hot enough, the zirconium reacts with steam to produce hydrogen gas and even more heat, which makes things worse. And if you still can't get water back onto the fuel, the uranium dioxide pellets themselves can start to melt. The melting point of uranium dioxide is around 5000 degrees Fahrenheit. That's what a meltdown is. It's the fuel literally melting, because decay heat has nowhere to go. So this is the scenario that played out at 3 Mile Island Unit 2. And the thing that makes it such an important story isn't just that it happened. It's how it happened, because it wasn't one dramatic failure. It was a cascade of small things, compounded by confusion, compounded by operators who were getting misleading information from their instruments and making decisions that, with hindsight, made things worse. It started with something mundane. The secondary cooling system, that's the non-radioactive loop, the one that takes heat from the steam generators and sends it to the turbine, had a problem. A maintenance crew had been working on a system called the condensate polisher, which is basically a water purification system. Some moisture got into an instrument airline, and it tripped the feedwater pumps. So suddenly, no water was flowing into the steam generators on the secondary side. Without that flow, the steam generators couldn't remove heat from the primary loop. Pressure in the primary system started to rise, which is exactly what you'd expect. The reactor scrammed automatically. The control rods dropped in and killed the chain reaction within seconds. That part worked perfectly. But now you've got all that decay heat, and the primary system pressure is climbing. A relief valve on top of the pressurizer, that tall, cylindrical vessel connected to the primary loop, opened to let off steam and bring the pressure down. And it did. The pressure dropped. But here's where the trouble really began. The valve was supposed to close again once the pressure came back down to normal. It didn't. It stuck open. And the indicator in the control room, it only told the operators whether the signal had been sent to close the valve, not whether the valve had actually closed. The light said the valve was shut. The valve was not shut. So now you had a hole in the primary system, and pressurized water, radioactive coolant, was streaming out through that stuck-open valve, pouring into a drain tank on the floor of the containment building. Meanwhile, the emergency core cooling system kicked in automatically, pumping water into the primary loop to replace what was being lost. This is exactly what it was designed to do. But the operators, looking at their instruments, saw something that worried them. The pressurizer water level was rising, and in their training, a high pressurizer level was associated with a dangerous condition called going solid, where the entire primary system fills with water, and you lose the steam bubble in the pressurizer that acts as a pressure cushion. They'd been trained to be very concerned about that. So they did what their training told them to do. They throttled back the emergency cooling pumps. They reduced the flow of the very water that was keeping the core covered. And this is where it gets really painful to think about, because what was actually happening was completely different from what the operators believed was happening. The pressurizer level was rising not because there was too much water in the system, but because the water that was there was boiling. The loss of pressure through that stuck-open valve meant the water's boiling point had dropped, and steam was forming throughout the primary system, pushing water up into the pressurizer. The core wasn't flooding, it was uncovering. The top of the fuel was being exposed, with no water to carry away the decay heat. For over 2 hours, the core was partially uncovered. Temperatures soared. The zirconium cladding reacted with steam, producing hydrogen. About half the core was damaged. Fuel melted, slumped, pooled at the bottom of the reactor vessel. It was, by any measure, a serious nuclear accident, the worst in American commercial nuclear history. And yet, and this is important, the containment building held. The massive concrete and steel structure that surrounded the reactor vessel did its job. Some radioactive gas was released, primarily xenon and krypton, noble gases that don't accumulate in the body. The radiation doses to the surrounding population were tiny. The average dose to people living within a 10-mile radius was estimated at about 1 millirem, which is a fraction of what you'd get from a chest X-ray. No one was killed. No one was injured by radiation. But the psychological impact was enormous. And you have to understand the context. The movie The China Syndrome, starring Jane Fonda, about a nuclear plant accident and a cover-up, had been released just 12 days before the TMI accident. 12 days. You couldn't script that timing if you tried. The public was already primed to be terrified. And then a real accident happened, and the communication from the utility and the government was confused, contradictory, and late. Pennsylvania's governor eventually advised pregnant women and preschool children within 5 miles to evacuate, and around 140,000 people left the area voluntarily. The images on television, the cooling towers of TMI, which were actually for the undamaged Unit 1, became the universal symbol of nuclear danger. The aftermath reshaped the industry completely. The NRC, which had only existed for about 4 years at that point, launched a massive investigation. The Kemeny Commission, appointed by President Carter, delivered a scathing report that identified failures at every level. The design of the control room instruments, the training of the operators, the lack of a clear chain of command during the emergency, the poor communication between the utility and state officials. The recommendations led to sweeping changes. Control rooms were redesigned to give operators better information. Training programs were overhauled, with much more emphasis on understanding the actual physics of what's happening inside the reactor, not just following procedures. The Institute of Nuclear Power Operations, INPO, was created by the industry itself as a kind of self-policing body to set high standards and conduct peer evaluations. Resident NRC inspectors were stationed at every operating plant, but the damage to public confidence was done. New reactor orders in the United States, which had already slowed to a trickle, essentially stopped. Every reactor ordered after 1973 that hadn't already been completed was eventually canceled. The economics, which were already brutal with the cost overruns and construction delays, became impossible in a climate of intense public opposition and ever-tightening regulation. Nuclear power in America didn't die overnight, but TMI was the moment the trajectory bent decisively downward. And here's the thing. The lessons of 3 Mile Island were absorbed. The industry genuinely did get safer. The changes in training, in control room design, in safety culture, in regulatory oversight, they were real, and they were substantial. American nuclear plants in the decades after TMI compiled a remarkable safety record. Capacity factors climbed from around 50 or 60% in the early 1980s to over 90% by the 2000s, meaning the plants were running reliably almost all the time. The number of unplanned shutdowns dropped dramatically. By the measures that matter for day-to-day safety, the industry improved enormously. But then, on April 26, 1986, something happened on the other side of the world that made 3 Mile Island look like a minor incident. At the Chernobyl nuclear power plant, near the city of Pripyat in the Ukrainian Soviet Socialist Republic, reactor number 4 exploded. And this wasn't a partial meltdown contained within an intact building. This was a catastrophic explosion that blew the 1,000-ton lid off the reactor, exposed the burning core to the open air, and sent a plume of radioactive material high into the atmosphere that spread across much of Europe. To understand Chernobyl, you need to understand that the reactor was a completely different design from anything in the West. It was called an RBMK, a Russian acronym that translates roughly to High Power Channel Type Reactor. And the RBMK had characteristics that no Western reactor shared, characteristics that made it uniquely dangerous under certain conditions. Where a pressurized water reactor uses ordinary water as both coolant and moderator, and where losing that water actually shuts the reaction down because you lose your moderator, the RBMK used graphite as its moderator. Huge blocks of graphite stacked together, with channels running through them for the fuel and for cooling water. The water in an RBMK was the coolant, but the graphite was the moderator. And this created a property that reactor physicists call a positive void coefficient of reactivity, which is a mouthful, but what it means is actually quite terrifying. If the cooling water in those channels starts to boil, if it turns from liquid into steam, creating voids, little pockets of nothing where there used to be liquid, in a Western pressurized water reactor, that would reduce the moderation and slow the chain reaction down. It's a natural break. But in the RBMK, the graphite is still there doing the moderating. The water was actually absorbing some neutrons, and when it boils away, you lose that absorption. So you get more neutrons hitting uranium, which means more fission, which means more heat, which means more boiling, which means even more reactivity. It's a feedback loop running in the wrong direction. More power makes more steam. More steam makes more power. That's what a positive void coefficient means, and it's the kind of characteristic that makes reactor designers in the West genuinely uncomfortable. Now, the Soviet engineers who designed the RBMK weren't fools. They knew about this property. They had operational procedures and control systems meant to keep the reactor in a regime where the positive void coefficient wouldn't become dangerous. And for years, it worked. RBMK reactors operated across the Soviet Union. There were over a dozen of them, and they produced enormous amounts of electricity. The design had advantages that mattered to Soviet planners. You could refuel an RBMK while it was still running, which meant higher capacity factors. You could build it without the massive steel pressure vessel that Western reactors required, because each fuel channel had its own small pressure tube. This made construction easier with Soviet industrial capabilities. And critically, the RBMK could produce plutonium for weapons as a byproduct, which had been part of its original appeal. But on the night of April 25th, going into April 26th, 1986, the operators of reactor number 4 were conducting a safety test. And here's the bitter irony. The test was supposed to demonstrate a safety feature. They wanted to know whether, during a power outage, the spinning turbine could generate enough electricity as it coasted down to keep the cooling water pumps running for the 40 or so seconds it would take for the emergency diesel generators to start up. It was a real safety question. There was a genuine gap in their emergency power coverage, and they wanted to prove they could bridge it. They'd tried the test before, and it hadn't worked properly, so they were trying again. The test required running the reactor at low power, around 700 megawatts thermal, which was already an unusual operating condition for a reactor designed to run at 3,200 megawatts. But things went wrong before the test even began. The power reduction was delayed by hours because the grid controller in Kiev needed the electricity, so the operators held the reactor at half power for much longer than planned. When they finally resumed the power reduction, an operator made an error, and the power plummeted far below the target, dropping to around 30 megawatts thermal. Almost nothing. And at that low power level, something insidious was happening inside the core. Remember xenon 135, that neutron-absorbing fission product that John Wheeler had predicted back at Hanford? At low power, xenon builds up because it's being produced by the decay of iodine 135, but it's not being burned away by neutron absorption the way it is at full power. The reactor was poisoning itself with xenon. The operators, under pressure to complete this test that had already been delayed, tried to bring the power back up by withdrawing control rods. They pulled out far more rods than regulations allowed. The operating procedures specified a minimum number of control rods that had to remain inserted at all times, what was called the operational reactivity margin, and the operators violated that limit. They were essentially flying the reactor with almost no safety margin, fighting against xenon poisoning at a power level and in a configuration that the reactor was never meant to operate in. And then they started the test. They blocked certain emergency signals that would have scrammed the reactor, because those signals would have interrupted the test. They reduced the cooling water flow to some of the pumps as part of the test procedure. And at 1:23 in the morning, when the test began and the turbine started coasting down, the reduced coolant flow meant the water in the core started boiling more vigorously. In a reactor with a positive void coefficient, that meant reactivity was increasing. Power started to rise. When the operators recognized something was wrong, the shift supervisor ordered an emergency shutdown, the AZ5 button, which was supposed to drive all the control rods back into the core. But here's one of the most devastating design flaws in the whole story. The RBMK control rods had graphite tips. The bottom portion of each rod, the part that entered the core first when you inserted them, was made of graphite, a moderator, not an absorber. Above the graphite tip was the boron carbide section that actually absorbed neutrons. So when you hit the emergency shutdown button and all those rods started dropping into a reactor that already had almost all its rods withdrawn, the graphite tips entered first, and for a brief moment, they actually increased reactivity in the bottom of the core before the absorber sections could follow. The very act of trying to shut the reactor down gave it one final push in the wrong direction. The power spike was almost instantaneous and absolutely enormous. Estimates vary, but the reactor may have surged to something like 30,000 megawatts thermal, roughly 10 times its rated capacity, in a matter of seconds. The fuel shattered. The cooling water flashed to steam so violently that the pressure blew the channels apart. There were at least 2 explosions, the first likely a steam explosion from the catastrophic pressure buildup, and the second possibly a steam explosion as well, though some researchers have argued it may have involved hydrogen generated by the reaction of steam with the zirconium fuel cladding at extreme temperatures, or even a small nuclear excursion. The 1,000-ton upper biological shield, the massive concrete and steel lid sitting on top of the reactor, was blown upward and landed at an angle, partially back on the reactor. The building was torn open. Burning chunks of graphite and reactor fuel were scattered across the roof of the adjacent reactor number 3 building and across the grounds of the plant. 2 plant workers died almost immediately from the explosions. Firefighters arrived within minutes and climbed onto the roofs to fight the fires, not fully understanding what they were walking through. Many of them received lethal doses of radiation. In the days and weeks that followed, 28 emergency workers and plant staff died from acute radiation syndrome. The total death toll, including long-term cancer effects in the broader population, has been debated for decades, with estimates ranging from the low thousands to much higher numbers depending on methodology and assumptions. The Soviet government initially tried to suppress information about the accident. It was Swedish monitoring stations over 1,000 kilometers away that first detected the elevated radiation levels and raised the alarm to the outside world. The city of Pripyat, home to nearly 50,000 people just 3 kilometers from the plant, wasn't evacuated until 36 hours after the explosion. Eventually, a zone of about 30 kilometers around the plant was permanently evacuated, over 100,000 people displaced from their homes. The cleanup was staggering. Hundreds of thousands of workers, called liquidators, were brought in over the following months and years. Some of them shoveled radioactive graphite off rooftops in shifts measured in seconds, literally running onto the roof, shoveling debris, and running back, because the radiation levels were so intense that a human could only tolerate brief exposure. Robots sent to clear the roof failed because the radiation damaged their electronics. Eventually, a massive concrete sarcophagus was built over the destroyed reactor, completed by November 1986, constructed by workers who themselves received significant radiation doses. That original sarcophagus was never meant to be permanent, and by the 2000s, it was deteriorating. A new confinement structure, an enormous arched steel structure, the largest movable land-based structure ever built, was slid into place over the old sarcophagus in 2016. So, what does Chernobyl tell us about nuclear power? Here's the thing, and this is important. Chernobyl was not a generic nuclear accident. It was specific to a reactor design that had known dangerous characteristics, operated in a safety culture that suppressed dissent, and tolerated procedural violations, within a political system where the nuclear establishment was essentially unaccountable. No Western light water reactor has the positive void coefficient that made the RBMK vulnerable to that kind of runaway power excursion. The containment structures that Western reactors sit inside, those massive reinforced concrete domes, didn't exist at Chernobyl. The RBMK had a building around it, but it was an industrial building, not a pressure-rated containment structure designed to hold in the products of a worst-case accident. But here's what Chernobyl did to the global conversation about nuclear power. It made the word nuclear synonymous with catastrophe in a way that TMI, for all its drama, never quite managed. TMI was frightening, but the containment held. Nobody died from radiation, and the actual public health impact was negligible. Chernobyl killed people. Chernobyl contaminated vast areas of land. Chernobyl created a permanent exclusion zone. And for millions of people around the world, Chernobyl became the defining image of what nuclear power means. Countries that had been building or planning nuclear plants reconsidered. Italy shut down its reactors entirely. Sweden voted to phase out nuclear power. Germany's anti-nuclear movement, already strong, gained unstoppable momentum. Even in countries that continued operating their plants, the political ground had shifted. And yet the engineering lessons from Chernobyl, like the lessons from TMI, did lead to real improvements. The remaining RBMK reactors were modified to reduce their positive void coefficient. Control rod designs were changed to eliminate those graphite-tipped rods. Operating procedures were overhauled. And internationally, The accident led to the creation of the World Association of Nuclear Operators, or WANO, in 1989, modeled somewhat on INPO in the United States, a global peer review organization where operators from different countries could share safety information and hold each other accountable. The idea was that a nuclear accident anywhere is a nuclear accident everywhere, that the reputation and future of the entire industry depends on every single plant operating safely. Which brings us to something worth sitting with for a moment. By the 1990s and into the 2000s, the existing fleet of nuclear reactors around the world, about 440 of them in over 30 countries, was quietly doing something remarkable. They were generating roughly 10 to 11% of the world's electricity, reliably, with extremely low carbon emissions. No air pollution, no greenhouse gases from the actual generation process. The capacity factors kept climbing. The safety record, measured in events per reactor year, kept improving. And as climate change moved from a scientific concern to a political and existential one, some environmentalists who had spent decades opposing nuclear power began to reconsider. Because here was this enormous source of carbon-free electricity already operating at scale, already connected to grids, already producing power around the clock, regardless of whether the wind was blowing or the sun was shining. The math was hard to ignore, but the economics had shifted too, and not in nuclear's favor. Natural gas had become cheap, especially in the United States after the shale gas revolution. Renewable energy costs were plummeting. Solar panels and wind turbines were getting cheaper at a rate that surprised even their advocates. And new nuclear construction in the West had become extraordinarily expensive and slow. When utilities in the United States and Europe tried to build new reactors in the 2000s and 2010s, Generation 3 and 3 Plus designs with enhanced passive safety features, reactors like the Westinghouse AP1000 and the French EPR, the projects became case studies in cost overruns and schedule delays. The Votel expansion in Georgia, the Olkiluoto 3 reactor in Finland, the Flamanville EPR in France, each of them years behind schedule and billions over budget. The reasons were complex and interconnected. A construction workforce that had lost nuclear experience during the decades-long building hiatus, supply chains that had atrophied, regulatory requirements that had grown enormously, first-of-a-kind engineering challenges with new designs, and the simple reality that these are among the most complex structures human beings have ever built. And then, on March 11th, 2011, the Earth shifted again, literally. A magnitude 9.0 earthquake struck off the Pacific coast of Japan, generating a massive tsunami that raced toward the northeast coast of Honshu at the speed of a jetliner. The wave heights in some places reached over 14 meters, 40 feet or more, and the devastation was almost incomprehensible. Nearly 20,000 people lost their lives that day. Entire towns swept away in minutes. And among the many things standing in the path of that water was a nuclear power station called Fukushima Daiichi, operated by the Tokyo Electric Power Company, TEPCO, situated right on the coast in Fukushima Prefecture. Now, here's the thing about Fukushima Daiichi. The plant had 6 boiling water reactors designed by General Electric, built between 1971 and 1979. These were Generation 2 reactors, workhorses of the same vintage as many plants operating around the world. When the earthquake hit, the 3 reactors that were operating, Units 1, 2, and 3, did exactly what they were supposed to do. The control rods inserted automatically, the fission chain reaction stopped within seconds, just as designed. The earthquake itself, one of the most powerful ever recorded, didn't break the reactors. That's actually worth pausing on. A magnitude 9.0 earthquake, releasing energy equivalent to roughly 600 million times the Hiroshima bomb, and the reactor cores shut down properly. The seismic engineering held. But you already know what comes next, because we've talked about this. Decay heat. That fundamental challenge of nuclear power that doesn't go away just because you've stopped the chain reaction. All those fission products sitting inside the fuel, cesium, strontium, iodine, dozens of others, continuing to undergo radioactive decay, continuing to generate heat. In the first moments after shutdown, that residual heat is enormous, maybe 6 or 7% of the reactor's full thermal output. For a reactor like Unit 1 at Fukushima, which had a thermal capacity of about 1,380 megawatts, 6% is still around 80 megawatts of heat. That's a tremendous amount of energy with nowhere to go unless you keep pumping cooling water through the core. And to pump water, you need power. The earthquake had knocked out the external power grid. Transmission towers toppled, lines down, the whole regional electrical infrastructure shattered. That's what emergency diesel generators are for. Every nuclear plant has them, big backup generators that kick in automatically when off-site power is lost. And at Fukushima Daiichi, the diesels started up. They were running. Cooling systems were functioning. For about 45 minutes, everything was working the way the backup systems were designed to work. And then the tsunami arrived. The plant's seawall was designed to handle a tsunami of about 5.7 meters. The wave that hit was estimated at roughly 14 to 15 meters at the plant site. It overtopped the wall easily, flooding the low-lying areas of the plant where, critically, most of the emergency diesel generators were housed, in basements and ground-level rooms. The seawater destroyed them. It also destroyed the electrical switching equipment that connected the generators to the cooling pumps. In a matter of minutes, Units 1, 2, and 3 lost all AC power. This condition has a name in nuclear safety: station blackout. It is one of the scenarios that reactor safety analysts worry about most, and it was happening simultaneously at 3 reactors. Now, the reactors did have battery backups, DC power that could keep some instrumentation running and, in the case of Units 2 and 3, operate a steam-driven cooling system called RCIC, the Reactor Core Isolation Cooling System. This clever system uses steam generated by the decay heat itself to drive a small turbine that pumps water back into the reactor. It doesn't need electricity. It's an elegant piece of engineering. And at Units 2 and 3, RCIC kept running for a surprisingly long time, roughly 3 days for Unit 3, even longer for Unit 2. But Unit 1 didn't have RCIC running. Its emergency condenser system, an older passive design called an isolation condenser, wasn't functioning effectively, and the operators, in the chaos and darkness of a plant with no power and devastated infrastructure, couldn't confirm its status. The batteries at Unit 1 lasted only about 8 hours. So picture the situation. It's the evening of March 11th, 2011. The entire region is in crisis. Roads are destroyed, communications are spotty, the plant is partially flooded, there's debris everywhere, and inside the reactor buildings, the operators are working in near-total darkness with flashlights, trying to read instruments that may or may not be giving accurate readings, trying to figure out how to get water into reactor cores that are heating up relentlessly. Decay heat doesn't negotiate. It doesn't wait for you to solve your logistics problems. It just keeps coming. In Unit 1, without cooling, the water level in the reactor vessel began to drop as water boiled away into steam. Within hours, Probably by the late evening of March 11th, the fuel rods began to be exposed. And when zirconium fuel cladding gets hot enough, above about 1,200 degrees Celsius, it reacts with steam in a chemical reaction that produces zirconium oxide and hydrogen gas. This is an exothermic reaction, meaning it generates even more heat, accelerating the damage. The fuel began to melt. By the early hours of March 12th, a significant portion of the Unit 1 core had melted and slumped to the bottom of the reactor pressure vessel. This was a full core meltdown, the thing that every nuclear safety system is ultimately designed to prevent. And that hydrogen gas, it was accumulating inside the reactor building. On the afternoon of March 12th, it ignited. The explosion blew the roof and upper walls off the Unit 1 reactor building in a dramatic blast captured on television cameras and broadcast around the world. It was not a nuclear explosion. That's physically impossible in a light water reactor, as we discussed way back when we talked about enrichment levels and critical mass geometry. It was a hydrogen explosion, a chemical detonation. But the visual was devastating. The world watched a nuclear power plant explode on live television, and the psychological impact was enormous. Over the following days, similar hydrogen explosions occurred at Units 3 and 4. Unit 3's explosion on March 14th was particularly violent. Unit 4's explosion was puzzling at first because that reactor had been shut down for maintenance with no fuel in the core. The hydrogen had apparently migrated through shared ventilation ductwork from Unit 3. Meanwhile, the cores of Units 2 and 3 also suffered partial meltdowns as their cooling systems eventually failed too. The operators and emergency workers at Fukushima Daiichi performed acts of genuine bravery during those days. They improvised desperately, at one point using car batteries scavenged from vehicles in the parking lot to power instrumentation. They eventually managed to get fire trucks to pump seawater directly into the reactors, a last resort measure that meant deliberately destroying the reactors to cool them, salting the cores with corrosive ocean water. The plant manager, Masao Yoshida, made critical decisions under impossible pressure, at times defying instructions from TEPCO headquarters in Tokyo. When he believed those instructions were wrong, he kept seawater injection going when headquarters wanted it stopped. Many analysts believe his judgment prevented an even worse outcome. Here's what makes Fukushima different from Chernobyl in a crucial way. At Chernobyl, the reactor itself exploded, blasting the core contents directly into the atmosphere in a massive, acute release. At Fukushima, the containment structures, while damaged and leaking, still provided a significant barrier. The radioactive releases at Fukushima were serious, primarily involving volatile fission products like iodine-131 and cesium-137, which escaped through venting operations, through leaks in damage containment, and through the hydrogen explosions. The Japanese government eventually rated the accident at level 7 on the International Nuclear Event Scale, the same as Chernobyl, based on the total quantity of radioactivity released. But the actual release was roughly 1/10 of Chernobyl's, and the nature of the release was different, more gradual, less concentrated. The human consequences were real, but require careful parsing. The earthquake and tsunami killed nearly 20,000 people. The Fukushima nuclear accident itself caused no direct deaths from radiation exposure in the immediate aftermath. Not one. The doses received by workers and the public were, with very few exceptions, below levels associated with measurable increases in cancer risk. But the evacuation, the displacement of over 100,000 people from their homes, many for years, some permanently, caused enormous suffering. Elderly residents died during the chaotic evacuation itself. The stress, disruption, and social dislocation contributed to what Japanese authorities classify as disaster-related deaths, numbering in the thousands across the affected region. The fear of radiation, in some ways, caused more harm than the radiation itself. And that's not a dismissal of the accident's severity. It's a recognition of how complex the consequences of a nuclear disaster truly are, extending far beyond the physics of fission products and dose rates into the realm of human psychology, social disruption, and institutional failure. The political fallout was swift and far-reaching. Japan shut down all of its nuclear reactors for safety reviews, all 50 of them, a fleet that had been generating about 30% of the country's electricity. The restarts have been slow and politically contentious. More than a decade later, only a fraction have returned to service. Germany, which had been gradually reconsidering its nuclear phase-out, reversed course entirely after Fukushima, committing to shutting down all its reactors by 2022, which it did, replacing much of that capacity with natural gas and renewables, but also, in the short term, with coal. Italy voted against nuclear power again. Switzerland decided to phase out its plants. Around the world, the Fukushima accident reinforced the narrative that nuclear power was simply too dangerous, too unpredictable, too unforgiving of human and institutional failures. But here's where the story gets more complicated and more interesting and maybe more honest. Because the years after Fukushima also saw something unexpected, a growing vocal movement of scientists, engineers, and yes, environmentalists arguing that abandoning nuclear power was itself a dangerous choice. The logic was straightforward. Climate change is an existential threat. Decarbonizing electricity generation is essential. Renewables are growing fast but face challenges with intermittency and storage. And every nuclear plant that closes tends to be replaced, at least in part, by fossil fuels. When Germany shut its reactors, its carbon emissions from electricity didn't drop as fast as they might have. When Japan shut its fleet, it burned enormous quantities of imported natural gas and coal to keep the lights on, and its emissions rose. So the conversation shifted, slowly, from nuclear versus safety to something more nuanced. Nuclear versus what? What are the real alternatives, and what are their real costs? Not just in dollars, but in carbon, in land use, in materials, in lives. Because fossil fuels kill